Dear friends, welcome to this Electrical Engineering Knowledge Sharing Channel AMP Power System. We are discussing about the asymmetrical short circuit current calculation due to unbalanced or asymmetrical fault. That asymmetrical fault we have considered line to ground fault, line to line fault, or line to line to ground fault. In this context, we have already discussed about the how to calculate this asymmetrical fault current, and to calculate this thing, what are the basic formula, what are the basic module is required, that we have already discussed. In the process, we have discussed how to unbalanced fault current and the corresponding unbalanced voltage and unbalanced impedance, how we can decompose into the balanced voltage, balanced current, and balanced impedance. In doing so, we have resolved this unbalanced voltage, unbalanced current, and unbalanced impedance into the positive sequence, negative sequence, and zero sequence current, voltage, and impedance. That we have already discussed. And in the last video, video number 60, we have discussed the various formulas required to calculate the unbalanced or asymmetrical fault current due to single line to ground fault, double line to ground fault, or double line fault, and the formula we have already discussed in the video number 60. And we have also said that in the next video, means today's video, we'll give a practical example, and from that practical example we'll calculate all these three fault current, that is the fault current due to a single line to ground fault, line to line fault, and double line to ground fault, using the basic modules of the impedances for the various loads and the basic formulas we have derived on video number 60 for calculating this fault current. So we are starting the same thing. Now we have considered a typical power system, which I have already drawn on the board, so that we can optimize our time, because we have to calculate three fault currents. It will take some time. To optimize the time, we have drawn the circuit diagram in advance. Now here we have considered a generator. First of all, this generator, this is a 11 kV generator that is connected to a transformer, a step up transformer, delta star transformer. The transformer is 11 kV by 230 kV, and then it is connected to a bus bar 1. This is called bus bar 1, and then this bus bar 1, then there is a line. The line has the impedance of 0.12 per unit, and then we have a transformer, star connected transformer. It is a 230 kV by 11 kV. It was 230 kV step up. Now we are stepping down to 11 kV, and from the 11 kV it is going to a motor of 11 kV motor. Now to convert the various impedances of this various power equipment, we have considered the base MVA is 150 MVA and the base voltage is 230 kV. Our basic consideration to convert all the impedance, these impedance are shown over here. These are on the basis of base voltage and base MVA. We have considered the base voltage is a 230 kV, that is your base voltage, and base MVA is a 150 MVA is a base MVA. Based on that, we have converted all these impedances in this per unit value. This is all our per unit value. So we can say generator has a subtangent reactance 0.1 per unit based on this 230 kV and 150 MVA. Zero sequence impedance of the generator is 0.016 and negative sequence impedance is 0.12. Subtangent impedance of that will be considered as a positive sequence impedance. These are only, we have neglected the resistance value, so we have considered only the reactance value. So all this reactance value we can put by J. It is all our J current. We know the resistance R, total impedance Z equal to R plus Jx. So as this part is 0, so this is only Jx part. This is the magnitude. The is will be put by J. This figure will be put by J figure. So it is all our reactance part we have only considered. Okay. This is all considered. J value on the reactance part we have considered, resistance we have considered 0. So this is the network we are considering. So first we will calculate the zero sequence of this SLG, single line to ground fault current, first we will calculate. So this is we have already considered base MVA, base kV 230 kV and base MVA 150 MVA. All the resistance has been considered zero, and all these impedances are converted as we consider the reactance only, and all are converted based on this kV and base MVA. That we have already seen in the during symmetrical fault current, how to convert the various per unit value or ohmic value to particular base MVA and base kV. That we have used the same formula and converted it. Now with this, first we will calculate this per unit. First we will calculate single line to ground fault. Now for the single line to ground fault, we have seen the formulas. SLG fault. What is the fault current formula? Fault current formula IF, that equals to, we have seen 3 VF. Okay, this is 3 VF divided by Z1 plus Z2 plus Z0 plus 3 ZF. We have already seen. Now here we have to say one thing. This generator has a voltage. We say voltage 1 per unit, that is a 230 kV. We are considering base voltage, that is 230 kV. We can consider as in this way. 11 kV generator, we are considering base voltage 1, and that is of angle of 0 degree. And it is a delta winding, you know, this is delta. So the delta A star to delta, when it convert, this is lagging by 30 degree. So that means if this is a 30 degree, if it is 0 angle, then this motor voltage will be 30 degree lagging. So it will be, what is the voltage? This voltage VF, here VF will be 1 into angle of 30 degree. So if it is 30 degree, then it will be lagging by 30 degree, so it becomes 0. It is at anti-clockwise, it was a 30 degree here. So this is a 30 degree over here. So when you convert to A star to delta, we have seen already it is 30 degree lagging. So this 30 degree lagging means clockwise it will go 30 degree, will come to 0 position. So this voltage will be 0. Another point we have to mention over here, we have already said that induction motor, or it is a, suppose this is a synchronous motor. So synchronous motor will be represented same as a synchronous generator. So it will be shown as a generator voltage and the corresponding impedance. That impedance is, this is the impedance. Okay. So that's why the generator voltage, the motor voltage is coming over there as a synchronous motor. So these are the basic formula for us. Now for the simplification of this formula, we have considered ZF equal to 0. This field reactance or the neutral field reactance, or the during the fault, on the earth fault path, what is the fault impedance coming? That is we are considering 0. We are considering the solidly earth fault. Okay. So this is your ZF equal to, we are considering ZF that equal to 0 in all this calculation to simplify the calculation. Otherwise it will be more complicated, more rigorous. We are considering ZF equal to 0. That means when the fault took place on the fault path, there is no impedance getting into picture. It is a 0. It is solid earth fault. Okay, that is we are considering in this way. Now from there we have already said that what, that the single line to ground earth fault current, this equal to, that means this is a, how we calculate this fault current. We have a voltage source VF, and then we have a positive sequence impedance, negative sequence impedance, and zero sequence impedance is connected like this way. We have already seen. In the case of sequence network, we have drawn in this way. Now, if we, that means it is your Z1, it is a Z2, it is your Z0. That is in that, then the corresponding current will be, and the voltage source is VF. Then the fault current formula is this. So in order to calculate the fault current, we have to calculate the Z1, Z2 and Z0. So for this network, first we will calculate the positive sequence impedance, the negative sequence impedance and the zero sequence impedance for this entire network. That is our first job. So let us calculate this impedance for the entire network. So to do that thing, we have to draw the each equipment individual impedance. So first we will draw the zero sequence impedance of this entire network. Now when we draw the zero sequence impedance, the generator zero sequence impedance, how it is? That is a generator, it has a, this is a 0, xn is 0. So this is your impedance of this generator, zero sequence impedance like this. And that value how much? Zero sequence impedance generator is a 0.06, right? This is the per unit value. Then we have a delta star winding. When delta star winding transformer is coming, then there is delta is open, zero sequence current cannot flow in the delta winding, so it will be open. Then we have a this transformer impedance, and that is a solidly connected, so there is no xn. So this transformer impedance, how much? It is a 0.15, right? Then we have a, this is a bus number 1. Then we have a line impedance, how much? That is equal to 0.12. All are connected in series, 0.12. Then we have again this transformer, it is a stress transformer, so it is a solidly connected, so it is how much? 0.15. Then we have a motor over here, so this motor, this is the motor impedance. Along with this we have a xn. You know, motor zero sequence impedance how much? That is equal to motor x0 plus neutral, this motor connection by through a neutral through a xn. Xn equal to how much? 0.1. So it was a 3xn. That means this is equal to 0.15, and 3xn means 0.3. It is all are j. All are j with a j. Because it is only reactance part. And then the neutral is coming back. It is connected over here. So this is where is our second bus? Second bus is over here. This is our bus number 2. Okay. This is our zero sequence network for this circuit, right? Now similarly we can draw the positive sequence network. Positive sequence this is a zero sequence network. Now how the positive sequence network? Positive sequence network, there will be voltage source. This is a voltage source VF, right? This is VF, that is equal to 1 into angle of 0. Then we have a positive sequence impedance of the generator. That is how much? That is equal to this one. Positive sequence impedance of the generator 0.1. This is 0.1. Then we have a transformer positive sequence transformer impedance 0.15. Then we have a line impedance 0.12. Here we have to mention one thing in the positive sequence network. After the generator, when we put the impedance, after the impedance we have a, what is that? We have a transformer coil. We can see in this way. It is connected over here like this way, right? Because we have shown this thing, all the secondary star winding has converted to primary to delta side, and that figure is 0.15. Then this is a line impedance. Then there is another transformer over here, that is equal to how much? 0.15. Then we have a motor impedance. This is the motor impedance, how much? That is equal to 0.25, right? And it is coming back. So when we made this equivalent, where is our bus? Our bus is over here. This is our bus 1, this is our bus 2. So bus 2 is over here. This is our bus 2. So if you draw this equivalent of this, how much it will be? It will be, this is a 0.1 and 0.5, how much? It is a 0.25, right? It is a 0.25. 0.25 this 2, and then it is coming with the bus 1, and then this sum of this 3. This is equal to how much? Positive 40 is 0.52. Then it is coming back. This is our, here is a voltage source VF. Positive, it is a positive voltage source. Okay, here is also a positive voltage source over here. How much? It is a VF, that is equal to 1 into 30 degree, right? And this is 1 into 0. That is our voltage source over here. VF equal to 1 into 30 degree. And this is equal to 1 into 0 degree. This is the equivalent positive sequence network. And then we'll draw the negative sequence network. After all, let us finish this 2 part. Now we go, now from this we can calculate the Z. Now we are considering, now we have to decide where we want to calculate the fault current. We are deciding to calculate the fault current on the, suppose in the bus 1 we have the arc fault. So at this point there is arc fault. So from this point, if we look into this, then how it will be? So this is our arc fault point. We can draw like this. This is our arc fault point. From this point we are looking the fault. In that case, what is happening? When you are looking the fault from here, the fault current, one part of the fault current will be flowing through this, another part is flowing through this. But here is a problem. This is delta is open, right? here delta is open. So what will happen over here? If delta is open, then this part will be coming over here. This current cannot flow through this, so the current will come and it back to the neutral over here. So our equivalent circuit for the single line to ground fault will be this part. So when we look into this, we are see the impedance. This part is one impedance and this is another impedance connected at this point by parallel circuit. So we have to calculate the equivalent impedance of this. Okay. So what will be the equivalent impedance for this? If we calculate this thing, you see here, now this is our bus 1. Now here one impedance 0.15 and here is impedance this 4. So 0.5, 0.30, 0.30 and 0.3, 0.6 plus 0.12, that means 0.72 J. This is our impedance and that connected in from this point we are looking into this. So these are connected in parallel. Okay, you are looking from here. So this is one part, this is another, these two connected in parallel. If you calculate the parallel of this, that is J015 parallel of J072 J. Yeah? That is what is this? Product of this into sum of these two. If you calculate this thing, this will come equivalent to 0.169. If you calculate this thing, this total value will be coming. This these two, if you calculate this parallel of these two will coming 0.124 J. That is the equivalent impedance of this zero sequence. So that means we can write down zero sequence impedance Z0 equal to how much? Z0 equal to, this is the value of Z0. Z0 value is 0.124. So we can write down this figure Z0 equal to 0.124. Okay. We got the Z0 value, zero sequence impedance of the entire network, Z0 equal to J 0.124. Okay. Now if you calculate the Z1 here, similarly if you see this is your Z1, if you calculate the Z1, these are two parallel, 025 and 052, you are looking from the fault point here. So these are two parallel. So if you calculate these two, you will get how much? If you calculate 0.25 into 0.052, you will get 0.169. You will get, this is the figure you will get from the positive sequence network. Okay, this Z1 value. Now, and with this voltage source of this. Now, if you go to this negative sequence network, then how it would be? If you go to the negative sequence network, this negative sequence network like a positive sequence network, in the case of negative sequence network, only the voltage source will not be present, right? So here what will happen? Here we have a generator impedance that is equal to negative sequence equal to how much? 0.12 we have said. So 0.12, that is negative sequence impedance of the generator. Then transformer is 0.15. It is all as J. Yeah? And then line impedance is J 0.12. Again transformer 0.15 J. Then we have a motor. Motor equal to how much? 0.27. 0.27 J. Then it is coming back. This is our fault point. Where is the fault point? Fault point is over here. So here also this is two parallel path. This is one parallel path and this is one parallel path. If you calculate these two parallel, you see here it is a 0.27 and it is 0.39. 0.39 plus 0.15. So if you can 14, 0.54. So there will be a one impedance over here. Then there is another impedance is connected over here. This is a parallel. This point we have the point of observation from here. So this is one path, this is another path. If you calculate this equivalent, this is coming 0.027 and this is 0.054. Yeah, 0.54 J, it is a J. If you calculate this parallel path, you will get Z2 equal to J 0.18. Yeah, J 0.18. You will get, this is the figure. So that is we have written over here Z2 is equal to, we can write down Z2 is equal to J 0.18. That is the negative sequence impedance of the entire network. So now we calculate these three impedance. Now easily we can calculate the single line to ground fault current, how much? Now single line to, in the case of single line to ground fault, we have shown that how easy it is. All these three positive signals, in the case of IF, we have write down already. IF equals to how much? IF equals to how much? 3 into VF by Z1 plus Z2 plus Z0 plus 3ZF, but ZF is 0, so this part is 0. So that is equal to, we can calculate 3 into VF equal to how much? VF is equal to, if you calculate 1 and 1, 0, ultimately resultant VF will be 1 into angle of 30 degree. That is the VF divided by how much? Z1 plus Z2. That means this sum, J into 0.124 plus J into 0.169 plus J into 0.18. So if you sum up this thing, how much it will come? Is 3 into angle of 30 degree angle by J. If you sum up this 3, how much it is coming? If you calculate this, it will be coming equal to your, in the case of zero sequence, it will be coming, your total value will be coming 0.477. Yeah, it will be coming 0.477. It will be coming 0.477. Okay, so if you multiply by minus j, then it will be minus j over here, and then it is minus j square means plus 1. So it will be minus j means minus 30 degree, right? Minus 30 plus 30 means it is 3 into angle of 60 degree minus by 0.477. That will be the fault current IF. It is a per unit, right? Now we have to calculate 1 per unit current means how much? Now our base MVA is a 230 kV and base MVA. So what is the per unit I base current? I base current equal to base MVA divided by root 3 into base kV, 230 kV. If you calculate, it is a MVA, base MVA into base kV. This is a kilo ampere, right? If you calculate, it will be coming 376.5 ampere. Okay, this will be the current IV. This is a kilo ampere, but multiplied by 10 to the power 3. Ultimately, you will get 376.5 ampere is the base ampere, 376.5. Okay, that will be your base current. So if we multiply this per unit value by base current, how much it will be coming? This current equal to coming how much? This is coming equal to your 6.34. This is coming 6.34 into angle of minus 60 degree. If you multiply 6.34 into this, the total fault current will be coming 6.34 into 376.5 into angle of 60 degree. This is equal to multiplied. If you do this thing, it will be coming fault current is equal to 2396 ampere. 2396 ampere angle of 60 degree minus. Okay, this will be the fault current for the single line to ground fault. So this is the way we will calculate the single line to ground fault current. Okay, so this is a single. Now we will go to the line to line fault. What will be the fault? So under this is it clear? So when we calculate the fault current, this is the fault current formula. We have calculated Z1, Z2, Z0 for the entire network. Then we have used the formula voltage source is 1, it is 0 degree and it's 30 degree, so it will be total 30 degree. Magnitude is 1 into 30 degree. And then these are the three impedance we have added. Then by calculation, we get this is the per unit current, 6.34 per unit based on the 150 MVA base and 230 kV voltage. Then we have calculated the base current in actual magnitude how much? Base current is equal to 376.5 ampere. So this per unit base current multiplied by the actual base current, we will get the net base current, that is we are getting 2396. This figure is this ampere is the fault current for the single line to ground fault at this bus. The moment you change the bus, automatically this magnitude will be different because the network will be different. So for each and every point fault, you have to draw the equivalent network and then you have to calculate the corresponding zero sequence impedance, positive sequence impedance and negative sequence impedance. From that you can calculate the current. So this is our single line to ground fault. Now we will go to the line to line fault. In the case of line to line fault, what we have seen, line to line fault, we have seen that positive sequence voltage. In the case of line to line fault, we have seen V1 equals to V2. Positive sequence voltage equal to negative sequence voltage, and the fault current equal to high mass. Fault current is equal to Vf into angle minus 90 degree divided by root 3. Here is a root 3 into Z1 plus Z2 plus Zf. This is the formula we have got. Now we have considered for calculation Zf equal to 0. If Z is equal to 0, then our fault current is Z1 plus Z2, right? So this is our the fault current for the negative sequence network. Now we know the Vf equal to how much? Now corresponding network, how it will be? Network will be, this is the Vf, and then this is the positive sequence network, then this is a Z2. It is coming back. This is a Z1 and this is Z2, and this is the Vf. It is a Vf. So if this is the Vf, this is the fault current is equal to this magnitude. So now you can put this value over here. So If equals to how much? If equals to root 3 into Vf is 1 into angle of 30 degree plus even angle minus 90 degree divided by Z1 plus Z2. Z1 equals to how much? Z1 is equal to 0.169 J plus negative sequence impedance J 0.18, right? If you calculate this is a 30 degree plus minus 90 degree, so it will be 60 degree. So root 3 into minus 60 degree angle divided by J into, if you add these things to, how much it will be coming? This two will be coming total. This will be coming in case of line to line fault. This will be coming 349. Okay, it will be coming J 0.349 if you add this thing. Okay, so if you multiply by minus J, then it will be minus J over here. J square is minus 1. Yeah, minus J square is a plus 1. So it will be equal to how much? J into root 3 into angle of minus 60 degree divided by 0.349. Okay, so J equal to 90 degree. So ultimately it will be coming root 3. It is a plus 90 degree. So minus 60 means angle 30 degree divided by your how much? 0.349. So if you calculate root 3 means 1.732. If you calculate this thing, it will be coming 4.96. 4.96 into angle of 60. It is a minus 90, right? Oh, sorry, it is minus 90. J is 130. It is a minus 90 and minus J 90, 60, minus 60 plus J equal to minus J means minus 90. So it will be 150. Yeah, it is minus J. Yeah, so it will be 150 degree. Yeah, angle. Sorry, it is a minus 60 and minus J means minus 90. So minus 90 and minus 60, it will be minus 150 degree. So it is minus 150 degree. 4. It is a per unit. Okay. Now this per unit magnitude, if we multiply the base current, we have got the base current previously we have calculated. Base current equal to IB equals to how much? IB equals to, we have calculated, IB is equal to 150 MVA divided by root 3 into 230 kV, right? Into 10 to the power 3. This is the ampere. That's equal to, we got is how much? It came to 376.5 ampere, right? This is the I base. So this 4.96, so this is equal to 4.96 into 376.5 ampere. If you multiply this thing 4.96, you will get the current equal to 1870 ampere at the angle of minus 150 degree. That is the actual ampere value. That is the line to line fault at the bus 1. Okay, so this is the line to line fault. Now in case of, so it is clear. Now we'll go to the next one, that is your double line to ground fault. In case of double line to ground fault, we have seen what we have seen in double line to ground fault. We have seen that again V1, in case of double line to ground fault, we have seen V1 equals to V2 and fault current IF is equal to 3I0. We have seen this thing in the case of a double line to ground fault, and also we have seen in case of double line to ground fault, the network, how it is connected. This is a positive sequence network. Okay, this is a positive sequence network, and the zero, then this is a common point, negative sequence in parallel to this, and then we have a 3 ZF plus zero sequence impedance. Z0, this is coming back. This is your negative. In case of double line to ground fault, the equivalent network, double line to ground fault equivalent network equal to this, and the corresponding fault current IF is equal to 3 into I0. That means in case of this case, if this is the bus, this is a Z1, this is a Z2, and this is Z0, and the fault current IF equal to kato? IF equals to 3 I0, means we can say in this way I1 plus I2 plus I0. That 3 equal to 3 I0. So all this current is flowing to this common point. All the current is flowing this way. Okay, that is this is a I1, this is a I0, and this is a I2. And the current I0 equal to IF equal to 3 I0. So now, if we want to calculate the IF, then I have to calculate the I0. I0 means the current flowing through this. Now we have considered ZF equal to 0 for our calculation. So this is equal to 0. This is not, it is solid. So the current, we have to calculate this thing. If we want to calculate that current, that means from this network, we have to calculate the voltage between this point. If I get the voltage here, suppose this network voltage is V0, then current I0 equal to V0 by Z0. Right? This Z0, we know that Z0 equal to 0.0124 for this network, entire network. So we can calculate Z, we know Z0 only, we have to calculate the V0. Now, when you calculate, if this is the VF, so how much voltage drop will be here? That is in proportional to the impedance. So VF, so we can write down the voltage across these will be, it will be drop in proportional to the impedance. So VF is the main voltage into proportional key. This is the impedance drop across this. Now the current sharing how much? When you look from this point, this path, this and this, these two connected in series in parallel to this. That means these two are parallel connected. When you look into this, the current is flowing through this way, coming back over here, and this current is going through this. So from this point, these are this parallel connected. You see here the current is, one current is coming, one current is going this way. So these are two parallelly connected, and that parallel combination is series with Z1. That means that is the equivalent impedance. That equivalent impedance proportional to the equivalent impedance, this voltage drop will take, VF will be drop over here. So that means we can write down Z0 parallel of Z2 divided by Z1 plus Z0 parallel Z2. This is the total equivalent impedance of this volt and that VF. Now this VF equal to how much? Angle 1 of 30 degree, right? We have seen this total voltage. So if this is the voltage and this figure, we know the Z0 equal to Z1 equal to how much? Z1 equal to 0.169. And this equal to how much? Z2 is equal to 0.18. And Z0 equal to J0.124, right? So if you do this parallel combination, you will get a figure of equivalent. I have already calculated this thing, and it will come as a 3 point, it will get 0.308 of angle of 30 degree. You will get, this is the figure V0, you will get the voltage of this amount. Okay. This is the voltage we will get from this figure V0. Now with this figure, we can calculate the corresponding current I0 equals to how much? I0 equal to 0.308 angle of 30 degree divided by Z0. Z0 equal to 0. I0 equal to, this is a V0 by Z0. Z0 J 0.124. That is your Z0, and this is the angle of 30 degree. Yeah? So again, if we multiply minus J, this will be minus J over here. That is a minus 1. So it will be minus J means minus 90. So minus, it will be 0.308 angle of 60 degree minus, because it is 30 and it is minus 90, divided by 0.124. If you calculate this through 2.44, 2.44 angle of 120 degree. Okay, this 0.308 divided by 1.24, you will get 2.44 into angle of 120 degree. That is a I0 value. So what will be the IF? So we can delete this part. IF equal to 3 I0. So IF equal to 3 I0 means this equal to 3 into I0 means this is the I0. So 2 point into 2.44 into angle of 120 degree. If you calculate this thing, it will come 7.33. Yeah, this will come 7.33 into angle of 120 degree. Now this is the per unit magnitude. So if you calculate this total value with our current, how much is our IB? IB we have already calculated, that is equal to your 376.5 ampere, right? That is the base current. So if you multiply this 7.33 into 376.5 with angle 120 degree, you will get this fault current equal to 2760 angle of 120 degree ampere. That will be your double line to ground fault current. Okay. So this is our calculation for this typical network for single line to double fault, double line to double line fault, and double line to ground fault. So it is a very clear to calculate any asymmetrical fault current, any power system, we need to calculate first the corresponding zero sequence impedance, positive sequence impedance, and the negative sequence impedance of the entire network using the sequence network of individual load, which we have already discussed. I am repeating it once again on video number 58 and 59. So without that sequence network or sequence impedance of individual load, we cannot calculate the corresponding impedance value of the entire network. Once we develop the individual equipment sequence network, from that individual equipment sequence impedance we calculate, and then we can draw the entire network based on the fault point. We can draw the equivalent network, and then from that equivalent network we can calculate the total overall how much zero sequence impedance, positive sequence impedance, and negative sequence impedance. Once we calculate this thing, then using these three formula, one is a zero sequence for this single line to ground fault. The formula is very simple. IF equal to 3 into VF voltage source divided by 3 sequence voltage impedance plus 3 into fault impedance. Okay. And in the case of double line fault current IF equal to √3 into fault voltage with an angle of -90 degree divided by Z1 plus Z2 plus ZF. And in case of zero sequence network, in the case of double line to ground fault, the fault current will be IF equal to 3 times of I0, and we have to calculate the I0 using this network, equivalent network, with the corresponding how much voltage drop taking place in the zero sequence impedance. Based on the zero sequence voltage drop, we have to calculate I0. Once we get the I0, then we will get the current IF equal to 3 I0. And we have a tool drawing the network V1 equal to V2. So if V1 equal to V2 means the positive and negative sequence network connected in parallel. That only then we can get the voltage between these two. But the current is unequal, but the voltage is equal means these two network is parallel connected. That is we have shown. From that we can calculate the zero sequence current, and then we can calculate the fault current. And we have considered all the base MVA and base kV, so we have to calculate the base current how much, and that per unit current will be multiplied the base current, we will get the corresponding short circuit current. So this is all about the short circuit current for asymmetrical fault. And with these 6 videos from video number 55 to 61, this video will be 61, we have tried to cover the symmetrical fault and asymmetrical fault current. And once we go through all this video, we will be able to understand what is a symmetrical fault current, how to calculate the symmetrical fault current, how to calculate the sequence component of the voltage, current, and impedance, how to draw the sequence network of individual load, then how to calculate the short circuit current for single line to ground fault, double line to ground fault, triple line or double line fault, using corresponding formulas. And finally, we can, using this simple example, we can follow this example to calculate this 3 type of short circuit current for a typical network. So with this, we are closing the short circuit current calculation session, and I hope if this helped to any one of you, I'll be feeling good. It will be my pleasure. So go through this. If we can help to you, that will be great. I have tried my best to make it a shortcut in the simple way to present it in the short, but it is a complicated thing, so you cannot make most, it is not possible to make more simpler than this, but I have tried whatever possible from my side. If it helped to any one of you, it will be my pleasure. Please go through this and look into this. But finally, I am telling once again, when we do the calculation for short circuit current nowadays, we are not using this manual process. We go through the computer and we do the data file, and then we run the program with the data file and the other using the ETAB or equivalent software, and we get all the in the short circuit current, because in the practical system this is not a limited bus. There are so many buses, various voltages, various equipment, so that is very complicated to do by manuals. Not that's why we use the computer, and we have to do the practice. If you want to do that practice, you have to need some training on that ETAB software from the ETAB owner or the company, how to do this thing. So various files you have to create first, and those files will be uploaded, and based on that file system with the software, it will calculate the short circuit current. So, but for the manual process, if you want to calculate a small system, this will be the short circuit current calculation. Okay, so that's all about today's session, and this is all about short circuit current calculation. I am closing this session today here, and please go through this. Thank you very much indeed, and thank you.